Hey everybody, welcome back to another round of astronomy. And yeah, let's get going. So we are going to start in that foray, that direction of studying the nature of stars. And so I thought I would give you a lecture about the historical development. Where did this come from? Where did the stellar classification scheme come from in the first place? So, the first thing I should mention, I'll start off with a quote here. Okay? The basic problem with the classification schemes, and I should put in parentheses, of stars, was that there was a lack of understanding of the physical basis for the classification procedures. In other words, astronomers did not know what were the important aspects of a star. How do I classify something when I don't even know what's important and what's not important? Okay? So that's kind of what the entire quote encapsulates. And I'll throw in some extra details here that astronomers had no idea about. We're in the 1850s to 1900s, that transition period around the turn of the century. And the astronomers are trying to classify stars, but they don't even know, for example, Wien's law. So we're already playing around with information in this class that astronomers had no idea about. Wien's law wasn't established until 1893. Additional difficulties. Helium had not yet been discovered. So a different way to say it is we don't even have a full understanding of the composition of the sun. Additional difficulties. There's these oddballs. You've heard the joke. You walk into the room and can't identify the patsy. That means you're the patsy. Wolf-Rayet stars are the oddball group. We have spectroscopy. We're studying the spectra of stars. And there's this weird classification of stars, this weird stars, that we now know are the patsy, the guys that are the oddballs. But at the time, we see stars that not only exhibit absorption lines, but Wolf-Rayet stars exhibit emission lines. Now, we won't spend much time talking about Wolf-Rayet stars, but at the end of the day, it's like a puzzle piece. It's like you're trying to put together a puzzle, and you have some pieces from a second puzzle that are in your box. And you're trying to figure out, well, does this actually belong here? I can't get it to fit anywhere. And it's not until once you have the complete picture that you realize that, oh yeah, that puzzle piece belongs somewhere else. That doesn't even belong in this puzzle. Some additional difficulties. The structure of the atom has not yet been well defined. It's not until 1911 and 1897, respectively, that the nucleus and the electron are discovered. So up until the 19th or the 20th century, we don't even know what atoms are made out of. And it's not until 1913 that we have the Bohr model of the atom, so that we can start conceptualizing why we observe emission and absorption spectra of various elements and consequently the stars in general. This again ties into a composition comment. Okay? So imagine trying to do all of this sorting without knowing the temperature of stars, the composition of stars, and not being able to explain the absorption or emission spectra. Okay? That's the kind of problem that we're faced with. So historically speaking, now this next couple of historical classification schemes you don't need to know unless you get really jazzed about it. Okay? The reason I give you these is because the final scheme that we use that was developed around the 1900s kind of looks funny. Okay? And I say looks funny, I'll give you the byline, not alphabetical. And so I thought I should give you an idea about why astronomers use a classification scheme that isn't alphabetical. So we go back to 1870s, and the 1870s, astronomers use pretty much the thing that they have available, color. Now bear in mind again, astronomers have no idea that the color of a star is indicative of the temperature. Okay? So they use a color scheme. They basically say, okay, well, class 1 stars, we are going to base off of whether they're color. They're blue or they're white. Okay? And they can measure the spectra, but they have no idea why that spectra is being produced. And so the canonical example for this would be Sirius. Okay? The class 2 stars were based on yellow. Okay? The canonical example of a yellow star, our sun. And so basically any star that resembled our sun, both in terms of color and the absorption spectra, those were labeled as class 2s. The third class, okay, so we've got blue or white, we've got yellow. You can guess what the third class is. Yeah, good. Red stars. And the canonical example of a red star would be something like Betelgeuse. Okay. So in the 1870s, fairly simplistic scheme, you have white or blue stars, you have yellow stars, you have red stars. So in 1889, it was recognized that the distinction of just class 1, class 2, or class 3 wasn't detailed enough. It didn't have a high enough precision. Or alternatively, we got better at distinguishing colors. And so the class 1, the white to blue, we suddenly broke up into finer distinctions. Rather than reusing Roman numerals, we ended up going alphabetical. So class 1 became class A, B, C, and D stars. White, bluish white, whitish blue, and blue. That kind of thing. Similarly, for class 2 and class 3, we broke them into finer distinctions so that we could be more precise with, classification schemes. Okay? And again, the key here is notice that these are alphabetical. So A through D is the previous class 1, E through L is the previous class 2, and then M and N are class 3. Okay? All right. Here's an image of Pickering's group, again at Harvard, and you notice that Pickering is standing here in the corner, and you notice that there's a wide disparity in this picture. And no, that's not by accident. Okay, Pickering, slight byline about the horrendous state of the workforce, of equality of wages. Just horrendous. And I'm sad to say this existed in Harvard back in the 1890s and unfortunately still persists today. So here's the issue. The reason for the disparity in this image is that at the time, the important part of astronomy is the data collection. In other words, the people that are the most important are the people that are actually collecting the data, taking the images, figuring out what to look at in their telescope, and using the photographic plates to take the data. Okay? The mundane, the unimportant work is the actual calculations and measurements. Okay? So the important things, the data collection, and then interpreting the data afterwards. The mundane stuff is performing the actual measurements, taking those photographic plates and classifying the stars, taking those photographic plates and measuring the parallax angle and the distance to those stars, taking those photographic plates and getting the data out of them. Okay? And so unfortunately, and yes, this is an actual term, sometimes women, first of all, were referred to as computers because they computed those values. They classified those schemes. And as horrendous as it sounds, computers were considered lower class work and therefore paid cheaper. Pickering hired women because he could hire more women for the same amount of money. So at least we get to start talking about a couple of personalities that really contributed to the advancement of astronomy. And frankly, without their contributions, you wouldn't have discoveries like Edwin Hubble later on in the future. Okay. So the first one that we're going to talk about is Annie Cannon. She's here in the foreground. Okay? And you notice that this device that she's looking at, what this is there's a light source embedded in the table, and then there's a photographic plate here. And so she's using a magnifying glass to actually see the photographic plate and where the spectra is displayed. And so adept did she get at classifying stars, she could do about 3 per minute. So she was really in the data, like to the point where she can look at a spectra and say A, B, C, D, blah, 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 blah. But after some time, she recognized that the alphabetical process, this classification of A through N, wasn't intuitive. Something seemed a bit off. And she recognized through digging in the data, through doing this classification day in and day out, she realized there was a better classification scheme, a better ordering. So Annie Cannon said, you know what, this A through N stuff, that's bogus. Okay? The real classification scheme, the real ordering, the real pattern I see is a classification scheme of OBAFGKM. In other words, she kept the old labels of alphabetical, and she realized that we need to reorder them. So A through N was already taken. She recognized that there's a new, even brighter, hotter category, and she called it O. So she inserted that first one as being the brightest. Then she realized, or brightest, I should say, the correct one. Then she realized that it's not the A-type stars that should be next, it's the B-type stars. And so on and so forth. Nowadays, we know this as going from high temperature to low temperature. Annie Cannon at the time had no idea that that's actually the pattern she identified. Okay? She just knew O-type stars, then Bs, then As, FGKMs. Okay? What Wien's law came out, then we realized, okay, this is according to temperature. A helpful mnemonic, this is how I remember it. Oh, be a fine gal or guy, kiss me. Okay? Now, if you don't prefer that mnemonic, that's perfectly fine. That's just the one that I've seen in pretty much every resource that I've looked at. Okay? You also notice that some of the classifications are missing. Annie Cannon identified that there were redundant categories. If you introduce this O-type star, you do the reordering scheme, you can get rid of, the D-type stars or the C-type stars. Those get absorbed into other classifications. But also her contribution was that she identified distinctions within a particular class. So what she did was she further subdivided each of these classes from 0 to 9. So she adds an Arabic number. So for example, I'll say you have an O5, we'll say an A5, and an A9 star. Okay. If I told you, in fact, take a minute, rank these stars from hottest to coldest. You got it? Yeah, good. And in fact, inadvertently, I didn't mean to do this. You notice it's already from hottest to coldest. So you first of all compare the letter, and remembering this ordering, okay, compare the letter. The first letter in that ordering is the hottest star. The next letter is the next, so you first of all look at the letters, and that will give you hot to cold. Now, if they have the same letter, like I've written the A5 and the A9, the next thing you need to go and compare is the number. Lower number, hotter star. Okay? Yeah, okay. And that's really all I have to say about that so far. Let me give you an idea about the spectra that Annie Cannon was actually working with. Okay? And you notice, for example, there are absorption lines that are absent in hot stars that appear in colder stars. Okay? There are lines that are present in hot stars that are absent in the cooler stars. Okay? So that hopefully that gives you just a sense of how difficult this task actually is. And we'll go through and explain, why is it that some of those lines show up? Why is it that some of them disappear? We now have a good mental model that we can explain that. For the Arabic numerals, okay, so she compared these to get the letter, but then how does she actually get the Arabic numerals after that? Now this part you won't need to you won't need to do, but I'm going to show you just to give you an idea. You notice both of these stars have absorption lines at the exact same locations. I've just drawn in some arrows to draw your eye to several of them. And you notice that they have the absorption lines at the same location. So what differs between these two stars? Yeah, good. How dark those absorption lines actually are. Okay. So not only is she comparing the location of the absorption lines, how large width of the absorption lines, but she's also comparing how dark those absorption lines are. And the darkness of the absorption lines is what tells her, is it a 0? Is it a 1, 2, 3, 4, 5, 6? So in some sense, she's measuring by eye how gray or how black an absorption line is to get the classification. So another question for you. Let's get some practice. Okay? Over here on the right-hand side, I have given you, again, the spectral type for each of the stars. So I've given you the spectra of each of the types of stars. And then over here on the left-hand side, I have given you 4 or 5 uncategorized stars. Go ahead, take a minute and determine which type of star I have. So in other words, Alpha Leporius, is that an O-type star? Is it a K-type star? Figure out what type of star it is based on the spectra. And do it for the rest of them. Yeah, you got it? Yeah, good, 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 good. And again, what we need to look at are the absorption lines for the star. Okay? So I'll go through, let's go ahead. Alpha Leporius. And again, I'm using the Greek naming convention. This is the brightest star in the constellation Leporius. I believe this is a southern constellation. This is the Latinized name of it. And so what we have to do, we have to go through, well, first of all, we notice right here on the right-hand side, we've got those 2 really strong absorption lines. And so right away, we should be able to exclude, say, these first 3 stars. These first 3 spectral types, that second line is not particularly prominent. So we know that it's not an O through A star. And then we keep going. We notice, okay, well, it's probably somewhere in here, this F through G. You notice that M, you start losing that. You start getting a bunch of those lines, you know, like the well-defined 4 lines seems to be absent. And again, you notice I say well-defined 4 lines. We have these other 2 dark ones. And so I would probably say even by the G-type star, you start losing that definition. So maybe even K. So my guess is that we should be somewhere around the F to G type star. Maybe an F or a G. I think I ended up saying F. Right. Yeah, that's me personally. But you should be in that F to G kind of area there. How about Beta Aquarii? Yeah, again, okay. Probably somewhere in the G to K range. That dark band in M is not there for this star, so my guess is that you're in the G to K range. I went ahead. I think I said G. Yeah, good. How about Alpha Lyra? Yeah, good, good, good. Now here, you get an idea about Annie Cannon. Not only is she looking at the location of the line, but she's also having to look at the width. And you notice Alpha Lyra as compared to Beta Tauri, right? The Alpha Lyra has more of that fuzziness to it. Okay? And you notice that really thin line there. Okay? That's not present in Beta Tauri. So my guess is that Alpha Lyra, I'd probably set that as an A-type star. Other one, while we're at it, Alpha Lyra, the brightest star in the constellation Lyra. Yeah, good. That's Vega, right? So you know that as Vega. Okay. How about Beta Tauri? Yeah, Okay, good, good, good. You get the really thin lines, which would probably indicate like an O-type star or maybe a B-type star, depending on how fuzzy that is. So I put it as an O or a B. And then lastly, Canis, Alpha Canis Minor. Yeah, I think I put that as a solid F again. Okay, good. Incidentally, Alpha Canis Minor, you'll know that as Procyon. So that's what Annie Cannon's doing. She's using this spectral classification to categorize stars. Okay. So the other piece that I want to give you is some idea why this pattern is being followed. Why are some lines absent from spectra, whereas they're present for others? And we actually have a really good idea about how that works. So I'll go ahead and focus in on this sodium iodide line for a second. Let's go through a series of questions, and that will work us through why some lines disappear and reappear at given temperatures. So let's say this. We're going back to the Bohr model of the atom, which again wasn't come up with until like the 1913. Okay, so Annie Cannon's not dealing with this until later in her career. So let's say for a second the 1 to 2 transition. So going from the lowest rung to the second rung. Okay? If that 1 to 2 transition corresponds to the absorption of 550 nanometer light, so that's visually yellow, what can you say about the wavelength for the 2 to 3 transition? Go ahead, take a minute, come up with the answer. You got it? Good, good, good. Now remember, the Bohr model, I'm using the distance between the rungs to indicate energy. Okay? So what I mean by that is that this jump requires more energy than this jump. And I'll put the 2 to 3. We'll do it as a chart. So more energy, less energy. Okay. Now the next question. Which wavelength corresponds to higher energy? Does short wavelengths correspond to high energy or long wavelengths? Yeah, good. Short wavelengths. So more energy corresponds to a shorter wavelength. Less energy, that's a longer wavelength. Okay. So now we're at a good point. If the jump from 1 to 2 is a shorter wavelength, or is more energetic, it must be a shorter wavelength. Therefore, the jump from 2 to 3 must be a longer wavelength. So the first piece is that this jump corresponds to some visible light. Theoretically speaking, conceivably, this jump could be such a long wavelength that it goes outside the visible part of the spectrum. Okay, next question for you. Here's the second question. So now we've got an idea, okay, that yellow light corresponds to a particular jump on the electron ladder. Second question for you. As the temperature of a star goes up, okay, what can you tell me about the number of electrons that are going to be in the second rung? Go ahead. You got it? Yeah, good, 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 good. So the second idea here is that as we heat up an object, what ends up happening is more and more of those electrons get some energy and are allowed to jump up to the second rung. Okay? So the idea, the hotter the object is, the more electrons can be on higher rungs. No longer are they stuck on the first rung, they could be on the second or the third. Okay? So as the temperature of an object goes up, more electrons are found in those higher rungs. So now let's take those two pieces and put it together. Okay? As more electrons are located on the second rung, what can you tell me about the absorption of the 550 nanometer light? Yeah, good. Remember, the absorption of the 550 nanometer light corresponds to a 1 to 2 jump. Okay? If you have less electrons on the first rung, there will be less electrons available to do that jump, and therefore there will be less electrons, or that absorption will decrease. And that's what we see here. As the temperature, let me get a different color here, as the temperature, let's do purple, increases, you notice that the absorption of that particular color decreases up until the point where it's simply no longer absorbed. Okay? These stars are so hot that there are no electrons available on that first ladder rung to absorb, to do that jump anymore. Or at least there's so little that we can't distinguish that absorption feature. Pretty cool, right? We're using that Bohr model to understand the stellar spectra. Well, you could say, well, Greg, okay, that's fine. That explains the sodium iodide. What about, say, something like the hydrogen beta line? But why is it not visible in some of these stars, the cold stars? I say, let's take the same idea, rinse, wash, and repeat. Here's what I mean by that. Imagine for a second that you again have your ladder rung. And the issue is to go from rung 1 to 2, let's say it requires so much energy to do that jump that the wavelength is so small that you are outside the visible light range. You're in like the ultraviolet light. So let's say that that's the first ladder jump. Okay. So for a cold star that's sort of warming up, this jump we can't actually perceive with our eyes or with our spectroscopic equipment. Now, as the star warms up, you have more and more electrons available in the second rung. And again, I should ask you, this is a large energy jump, which corresponds to a shorter wavelength. This is a less energetic jump, which means the wavelength is longer. So short wavelength, this lower energetic jump, this is a longer wavelength. And that means that we're moving closer and closer to the red end of the visible spectrum. Okay. So this jump, for example, as the temperature goes up, this jump might actually correspond to visible range of light. And then you get to the third rung where, again, that jump is so small in terms of energy, that's, off of the visible light range again. This could be like infrared, infrared, IR. Pretty cool, right? So that's why you can get some of these lines that are not available for the low temperature stars, but then pop in for the high temperature ones. So in any case, that I think is enough for this lecture. Please keep writing down your questions, bring them to class. Thank you for your attention. I'll see you next time.